Hello, my name is Brendan Zemper,
And I'm Katie Henschel.
and we are students with the University of Wisconsin-Eau Claire, and today we will be giving a presentation on the mathematics of introductory cryptography for the Math Retreat of 2020.
In this presentation, we'll be going over the history and encryption processes for the ciphers shown, as well as the analysis of the math. We've broken it into substitution and transposition ciphers to give a basic understanding of the math involved with these two types of hand ciphers.
So, as an introduction to the math that is used here, ultimately a cipher is a way of hiding or encrypting and revealing or decrypting text. So first we need a group in which we can perform operations. So let A be a group containing every letter in the English alphabet on addition. So since there are 26 elements, this is isomorphic to Z mod 26, where A is equivalent to 0, B is equivalent to 1, and so on and so forth, and Z is equivalent to 25. Now, like Zmod 26, we can add to these elements. So A plus 2, for example, is 0 plus 2 in modulus 26, which is 2, which is the letter C. Similarly, the alphabet loops back around to A at the end. So if we have Z plus 1, for example, we have 26 mod 26, which is 0, which is the first letter in the alphabet A. So now a word or a string of text can be defined as some kind of value in the nth dimension of A, where we have A sub 0, A sub 1, all the way out to A sub n minus 1. This is a word. And now a cipher is mapping a string of text in this group to the exact same group, just slightly modified. So a function f from A super n to A super n.
The first type of cipher we will be analyzing are substitution ciphers. The substitution cipher maps each letter in the text to a different letter to make it unreadable. However, these ciphers are vulnerable to frequency analysis. Frequency analysis takes advantage of how often letters occur in a language. For example, letters like E appear more often than Z, which can be used to a codebreaker's advantage when dealing with these types of ciphers. These ciphers originated in ancient Rome, one of the most famous being the Caesar cipher, which we will discuss next.
The Caesar cipher was originally used by Julius Caesar in the 1st century BC. Julius Caesar wanted to be able to communicate with other generals in his army, and he wanted no one else to be able to understand what was being communicated. He wanted it to be secret. So he made this cipher as a way to achieve that goal. What made this cipher secure was the fact that most people in that era were not literate. And those who were, who may intercept the messages he was trying to send, didn't exactly know what was being said because ciphers were so uncommonly used back then. Nowadays, this cipher is seen as very insecure and is used more as playful, informal settings of encryption where security is not very important. In ancient Rome, this was implemented using a cipher wheel as shown here, where there is two alphabets, an inside and an outside ring, where the inside ring can rotate to match up one version of the alphabet to a shifted version of the alphabet. So the way that the Caesar cipher works is that we take in a key, which is some integer, and we shift every single letter of our plaintext by that key amount. So, for example, if we take the text math retreat and encrypt it with a key of 3, then M, 3 letters after M, is N-O-P. And so the first letter is P. Similarly, with A, we end up with E, and so on and so forth to end up with this string of text that makes no sense in context without the understanding that we're using the Caesar cipher. As a fun fact, the key of 3 is exactly what Julius Caesar used for his encryption. For decryption, instead of adding, it's the exact same thing but subtracting, where if we have a key of 1, we go backwards one index in the alphabet for each letter in the ciphertext. So N would go to M, B to A, etc., to end up back with math retreat with the given ciphertext seen there below. As another fun fact, Augustus Caesar used the Caesar cipher as well, but with a key of 1, as shown here. So looking at a mathematical definition of this cipher, we have same thing as before, a key k, which is some value in the set of integers. So now, having this fixed key, we can define the Caesar cipher function with sub k is a function which maps a super n to a super n. And this is defined by taking each letter of the plaintext and adding k to that value modulus 26, as described below. Now, this function is invertible, surprise, since every cipher it needs to be able to be decrypted in the exact same way that it was encrypted. So we see that for each p sub I in the plaintext, that value is equal to that same letter in the ciphertext minus k in mod 26. We also see that this function is bijective. The proof of such is omitted. As an example, if we take the word cat, the letter CAT, with the Caesar cipher of a key 13, we add 13 to each individual letter of the plaintext, so C plus 13, A plus 13, T plus 13, carry through on the mathematics of that to end up with 15, 13, and 6, which ends up with the letters P, N, and G. And so this is our ciphertext. A key of 13 is also commonly referred to as the rote 13 cipher, in which encrypting and decrypting is the exact same, since there are only 26 letters in the alphabet.
In the late 1500s, Mary Queen of Scots was killed for treason because her cipher was broken by the government. As a result, the idea of using multiple alphabets was conceived in order to ensure security. Hence, the Vigenère cipher is the first polyalphabetic substitution cipher. The credit for the cipher was given to Blaise de Vigenère, although the first known person to write about this idea was polymath Leon Battista Alberti in the 1400s. To encrypt a message with the Vigenère cipher, it requires a keyword which will be used to shift every letter in the plaintext by each letter of the keyword's numerical value. For example, the letter A requires a shift of 0, B is a shift of 1, and so on and so forth. Below is an example detailing this process. As you can see, the keyword math is repeated above the plaintext with every letter in the keyword aligned with the letter in the plaintext. Then each letter in the plaintext is shifted by the numerical value of the keyword above it, resulting in a cipher. To decrypt the cipher, the same process is repeated in reverse. The keyword is aligned with the ciphertext and is shifted backwards by the numerical value. Thus, y, which has a numerical value of 24, is shifted backwards by the value of 2 in order to become 22, which is w in our alphabet. This process is repeated for the rest of the cipher. For the math of the Vigenère cipher, we will begin by fixing a k in m dimension of a such that k is a word within a sub m. Then we'll define Vigenère as a mapping from a to the n to a to the n, where inserting the plaintext into the Vigenère map results in a ciphertext such that each c is the value of p plus k sub I mod m, which is then mod 26, meaning that it will be within the alphabet. Then to decrypt the Vigenère cipher, the math follows similar logic where the inverse of the map is also defined as a to the n to a to the n. Then inserting the ciphertext into the inverse of Vigenère results in the plaintext where the function is c sub I subtracted from k sub I mod m, which is all then mod 26 to make sure the value is within the alphabet again. Moreover, the Vigenère cipher is also bijective, meaning each letter is only mapped to one letter and each letter is accounted for.
So next, we have transposition ciphers. Substitution ciphers changed each individual letter by adding some sort of value. In contrast, transposition ciphers reorder the letters that are already there in some kind of prescribed way that can be reversed. So this is not unlike the substitution ciphers, where it is completely vulnerable, but in different ways. It is vulnerable to brute forcing keys and by testing every word in a dictionary. It is also vulnerable to more complex statistics, like quadgram statistics, and analyzing segments of letters in the English language. This originates with ancient Greece in the 3rd century BC with the sky tail, where a leather binding is wrapped around some sort of cylinder, and the plain text is written horizontally, ending up with a scrambled message that the receiver would be able to decrypt by wrapping the leather binding around a cylinder of the same size. The first transposition cipher we're looking at is the columnar transposition cipher. This cipher was used very frequently in the first part of World War I, where the Germans used it to encrypt all of their communication in the nautical field between submarines. This was ultimately cracked by the British because of one fatal flaw that the Germans overlooked. They often reused keys or used keys that were easily guessed or familiar to the individual who was encrypting it in the first place, such as the name of a parent or a significant other. So eventually, the Germans stopped using the columnar transposition cipher, but it was revitalized in World War II in the form of the double columnar transposition cipher, where the columnar transposition cipher was simply used twice with different keys. This fixed the issue of reused keys and made it a little more secure, and we see that it was used by a lot more countries during this time. So the columnar transposition cipher is broken up into 3 steps and is a little more complex of a function than with the other ones we've looked at so far. So as before, we take in a word as a key, and then we ultimately transpose columns of a matrix according to the ordering of the letters in the key. So breaking that down, we first make a matrix in which the number of columns is the length of the key and fill in our plain text horizontally. Then we transpose the columns according to the ordering of the key, putting the earliest letter in the first column, second earliest letter in the second column, etc. Then the ciphertext is read down in the order of the columns. For decryption, it's the exact opposite. So as an example, if we have the text, the quick brown fox jumps over the lazy dog, and a key of math, we make a matrix that has 4 columns, hence the key math, and we fill in the plain text horizontally. Then, since A is the first letter in our key, we then move that entire column over farthest to the left. H is the second letter, and so we move it to the second column, etc. And then we read off our ciphertext down in the order of the columns. And so the first few letters of our ciphertext is the first column of that second matrix, H, I, R, F, etc. And we keep reading down the columns to form our ciphertext. Note that our plain text wasn't able to fill the matrix entirely, and so in this example, an underscore was used to fill in that space. This is just convention. It is also just as acceptable to use the letter X or Y or Z or really anything you want, as long as something fills in that space. So looking at the math for this, we have to first suppose that we have a key that is n letters long and a plain text that is L letters long. And so then the number of columns that we use is going to be equal to this other value, m, that is equal to the ceiling of L divided by m. Now, in order to fully define the columnar transposition cipher, we first need to define another function. We're just calling it the min function, which takes in 2 values, a natural number and a word, and we are defining it as the minimum of sub k of an entire word is equal to the kth smallest letter in that word. So if we have 0 as our input, we're taking the lowest number in our key, and if we're taking 2, we're taking the second lowest letter, etc. So now we can fully define this function. So our cipher columnar sub k is mapping a word of length L to a word of length L, and we are defining it as the composition of three different functions: rho, psi, and kappa. Rho is mapping our word to a matrix with the dimensions m and n, just according to the values in the row. Psi is mapping the matrix to another matrix defined by the ordering of that min function that we saw earlier. We're just transposing those columns. Note that this is the same as multiplying our original matrix by some other elementary matrix. Our last function, kappa, is mapping our matrix to a word again, according to the columns in our matrix. And so, as seen here, this is the same thing that I just said. Rho is filling in the matrix horizontally, psi is transposing the columns, and kappa is reading off the columns vertically.
The last cipher is the railfan cipher. The cipher was actually used by both sides to send messages during the U.S. Civil War. It had actually remained a popular way for civilians to send messages until the 1950s. However, it is fairly easy to crack since there are an extremely limited amount of keys, and there are now powerful anagram tools that can crack the message quickly. To encrypt the message, a number value for the key must be chosen. For this example, we will use the number 3. Then the plaintext will be written out in 3 rows where the first letter is placed on the first row, and each letter preceding that is placed on the row below it until it reaches the bottom, where the next letter will be placed one above it. This results in the zigzag formation shown on the slide. After doing this for the length of the text, the ciphertext is completed by transcribing row by row. Finally, for the math portion, the railfan cipher is a route cipher, meaning that it is placed into a matrix and encrypted by traversing through a predefined route, as we have shown in the previous slide. Moreover, the plaintext is filled into a matrix with k rows in a cyclic manner and read out of the matrix by row. A cycle length is defined as 2 times the key minus 2. Then the letters on the first row are 1 mod 2k minus 2, and the last row are k mod 2k minus 2. Lastly, in order to decrypt the cipher, let L be the length of the ciphertext and K be the length of the key. Then dividing L by K results in the amount of letters in each row, and then L mod K results in the amount of letters in the last row. Thus, writing out row by row will get the plaintext.
So thank you all for listening to our presentation. Again, my name is Brennan Zember, and I'm here with Katie Henschel, and here are our resources for this presentation.